everyone, and welcome to Keeping Tabs on Chemistry. In this video, we're going to be discussing phase diagrams. So a phase diagram is a diagram that relates the phase of a substance to the temperature and pressure. So before we've talked about phases in terms of temperature alone. Well, that's convenient when we're at standard pressure, but we're not always at standard pressure. So we need a more flexible graph, something with more information to help us know what phase we're going to be in. So in a phase diagram, any point along a line represents a state of equilibrium between two states of matter separated by that line. That is where a phase change is happening. So on a phase diagram, the three phases are easy to identify by the three sections in terms of temperature. We know that solids have the lowest temperature, gases have the highest temperature, and liquids are going to be in the middle. So along any of these lines between solid and liquid, if we're going from left to right, we are melting, but liquid to solid would be freezing. Liquid to gas is vaporization, which we know more commonly as boiling, but it can be evaporation as well, so we generalize it as vaporization. Going from gas to liquid is condensation. Now, solid directly to gas, notice it does not go through the liquid phase, that is sublimation. Gas directly to solid, skipping the liquid phase, is deposition. So there are a couple interesting points in a phase diagram. The first one is the triple point. The triple point, represented by A here, is the temperature and pressure under which all three states of matter occur at the same time. They exist in equilibrium with one another for a particular substance. That means at the same moment we can have all 6 phase changes happening together with all 3 states of matter. Now that might be hard for you to kind of wrap your head around, so I'm going to go ahead and play a video here of a triple point of cyclohexane being established. So right now it's in a vacuum. It's very hard to get to the triple point because you got to make sure it's at exactly the right pressure and temperature. So cyclohexane is the easiest one for us to achieve in lab. So here you can see it kind of freezes over. They're fiddling with it a little now before we can get it to the triple point, but eventually you're going to see that solid start to boil. Oh, here we go. There you go. And it goes between liquid and solid and gas, and it's interchanging between all 3 phases at the same time. So that is what a triple point looks like, which is very cool. Now, we can also find the normal melting and boiling point based on a phase diagram. Now, I say normal melting and boiling point. The normal melting point is the temperature at which the substance melts at exactly 1 atmosphere of pressure. So this is talking about the melting point at sea level is the normal melting point. Same thing with normal boiling point. It's the temperature at which a substance boils at 1 atmosphere of pressure. It specifies that we're at standard pressure. Now, we've talked about before how at different altitudes where there's different atmospheric pressure, you have different temperatures of boiling. So this is a way of kind of standardizing. When I say normal melting point, I mean the temperature at 1 atmosphere. So if you wanted to know normal melting point, you could find wherever 1 atmosphere is on your y-axis, come across and find the temperature of this melting freezing line. Remember, melting point and freezing point are actually the same temperature. Melting and freezing occur at the same temperature. So you would come down and see what temperature that occurs at. Similarly for boiling, right, you would come across to the vaporization and condensation line and see what temperature that occurs at. There's one last point which is a little interesting. It's called the critical point. The critical point is the temperature and pressure beyond which the liquid and gas phases are indistinguishable, and the substance becomes a weird kind of hybrid that we call a supercritical fluid. You'll notice up here in the right hand corner how they kind of blend those two colors together. The line stops. So kind of if you make a box here, any temperature pressure combination in that box is a supercritical fluid. So it's hard to imagine a supercritical fluid as well. So I'm going to jump this ahead to here. Here you can see they are raising this liquid to above its critical point. So you can see it boiling, then eventually the line separating the liquid and the gas just kind of disappears. Now it's a supercritical fluid. Now, as they cool it down, it ends up being opaque for a couple of different reasons, but as they keep cooling it down, eventually you get beyond that range of supercritical fluid and it goes back to condensing as a liquid. Right? Very kind of cool chemistry going on there. So here are examples of two phase diagrams. One is for water and one is for carbon dioxide. You'll notice a couple interesting differences and similarities here. So point O on both of these is the triple point. So for water, the triple point occurs at 0.81 kilopascals and 0.01 degrees Celsius. Very close to freezing. For carbon dioxide, that triple point occurs at 518 kilopascals and negative 56.6 degrees Celsius. So you can see how it's different for different substances. Now, if I look at 101.3 kilopascals, that's atmospheric pressure, standard pressure. 101.3 kilopascals across, I can see here I would hit a melting point for water at roughly 0 degrees Celsius. Here I hit the boiling point at 100 degrees Celsius. I know that about water. But if you look at carbon dioxide, the 101.3 kilopascal line only crosses one phase change, and that is sublimation and deposition. Notice carbon dioxide never melts or boils at atmosphere or standard pressure, which means that carbon dioxide does not have a normal melting or normal boiling point. Instead, we can see that it will sublime or deposit at standard pressure at negative 78.5 degrees Celsius. Now, we've actually seen this in class with dry ice. We've seen dry ice subliming at standard pressure at sea level, and it was very, very cold. We couldn't touch it. That's because that temperature was very, 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 very low. The other notable difference here, and this is special for water, water actually has a backwards solid liquid line versus with a negative slope. Most things like carbon dioxide and almost everything else has a positive slope on their solid liquid line. You don't need to worry about that so much as just being able to identify where solid, liquid, and gas are, where the triple point is, where the critical point is, and how to find normal and uh, boiling and melting point. So, based on the phase diagram, answer the following questions. Go ahead and pause the video, see if you can answer it. All right, looking at A, is there a normal melting or boiling point present? Well, this is in atmospheres. So down at 1 atmosphere, which is standard pressure, right, it only crosses the solid gas line. So no, we do not have a normal melting or boiling point. It says, what is the pressure at the triple point? The triple point is right here. So the pressure, it tells me, is 5.2 atm. What is the temperature of the critical point? At the critical point, I come down to temperature, and it is 31 degrees Celsius. What phase change can occur at 1 atmosphere? So at that 1 atmosphere, the only phase changes that can occur are sublimation and deposition. And that concludes our lesson on phase diagrams.